Hello again. This is another exciting episode of C++, CIS 2252, and I'm your host, John Baugh. We are in Chapter 8 today. It's technically Session 7. I don't count the midterm as a session, quote-unquote. If you've taken your midterm, your grade is already posted. Once I get all the midterms in, we'll hopefully go over it. I went over it with several of you if you had requested that I grade it while you were there, so many of you already knew what your grade was. Today we are going over pointers, which is a really interesting subject within C++ because you typically don't have to deal, at least directly, with pointers in a language like Java, for example. Java hides a lot of the details of pointer variables and referencing. So in C++, though, you have to be very aware of what you're doing with pointers. It's one of the most powerful, but it's also a very, very challenging topic within C++. So first things first, we'll go over the syllabus just to see where we are. So this lecture is for the week of 6/24. Last week was arrays and vectors, and I assigned the second programming assignment. Programming project 1 is due this Friday, so the 21st at 11:59 p.m. So if you're keeping up on this, I hope you're paying attention and keeping up on the lectures. I have been visiting the discussion boards. I think there was a glitch in the system because I really did not see a couple of the posts that had been posted, it seems, several days ago. I have been checking the site regularly, so I'm not sure quite what happened there. But I did respond to them, so if you posted, make sure to check your responses. A couple questions about the programming project involving the multiplication. You are not to write the logic of the code inside of main. Okay, the whole point to this project, or the major point to this project is using functions, being able to use functions and call them. Likewise, you are not to put cout and cin statements inside of the multiply positive function that you devise to ask the user for input or do the calculations in there. It should not be a void function. It should be a value returning function. All right, so that's one of the things I wanted to mention about the project. The midterm went pretty well. I think most of you did pretty well on it. If you got, say, below an 80%, I would highly recommend studying extra hard or going over what you did wrong, contacting me if you need a little bit of extra help. Because some of those problems were essentially gimmies. I basically told you what the problems would be before the test. So if you really didn't understand them or are not taking the time to do them, then you might be having some problems in your programming assignments as well. A few people have turned in their programming assignments already. I won't start grading them until I get more in, or the majority of them in, after the actual due date. But I do appreciate it if you have turned it in early. That's good, and that shows that you're really on the ball with things. So if you have any further questions about the programming assignments, I will attempt to check the discussion board frequently over the next couple days. Anyway, today's topic is pointers. So it's Chapter 8, and it's on pointers. And what is a pointer? Well, a pointer contains the memory address of a variable, okay? And then that variable contains a specific value, okay? We've used variables before. So if I have Visual Studio open, and I have C++ here, I've got int a equals 5. That is a variable, what we call direct referencing. Okay, it's called direct referencing. That's because a actually contains this value 5. All right, A contains the value 5. That's called direct referencing. The A is a variable of type integer, and it contains the value 5. So when we use pointers, we use something called indirection. So let me make a pointer variable and show you what we can do with it. So int pointer, now that little star symbol is when you hold down shift and hit the 8 key, that gives you the asterisk. That's the star symbol, and that's the symbol we use for pointer, declaring a pointer variable. And I'm going to call it a PTR for a pointer, and I'm going to initialize it to a special value, which is the 0 value for pointers, called null. Now, in Visual Studio 2012, you can use the value null pointer, null PTR, because it supports the C++ 11 standard. Okay, if you get an error in whatever compiler you're using, or it doesn't recognize this null pointer, just use the capital word null, or you can even use the value 0. That's actually an acceptable value. I would recommend for pointers 0 values, use the word null or null pointer if you can, null PTR. Notice it turns blue here in Visual Studio 2012. That's because it is a keyword of the C++ 11 language. It was not available in previous versions of C++, or in the previous version of C++, which the standard had been in place for over a, well, actually I'm trying to think here, probably a couple decades, or a decade or so. So it hasn't been updated for quite a while, the C++ standards. The original C++ was in 1986, and then later on in the 90s, yeah, so I guess that's been a couple decades almost since they've updated the standard. Then they just updated the standard, and it's called the C++ 11 standard because it's C++ 2011 was when the standard, I believe, was formalized. But it has taken a couple years for compilers to catch on. So I'm not sure if Xcode supports the new standard. Knowing Apple and their love of standards, it probably is. But if it isn't, just use null or 0. It's fine. Okay, so we've got that. Now that's how I initialize the variable. Now I can use I can use what's called indirection by first I want to point to this variable a. So you would agree that when I create this variable, what the compiler does is that it creates memory to hold an integer. When I say int a, as soon as I say that, the compiler knows it has to create enough memory to hold an integer. Okay, and then I put the value 5 inside of it. Right? I store this value 5 inside of the variable a. Okay, that's the direct referencing. A is the value 5. It directly references the value 5. A pointer likewise does take up its own memory, but a pointer is a special type of variable. This would be an integer pointer, so that means whatever this value is can point to null, which is kind of a universal value for 0 in pointer languages, or in terms of pointers. But I can point to any integer. So don't think of this as an integer. All right, think of this as a pointer to an integer. Now, what I can do is I can say a PTR is equal to, and then I use a special symbol. We've seen this symbol before in a different context for passing by reference, but in this context it's called the address operator or the address of operator. If I use the and symbol, which is shift 7, okay, on the keyboard, that gives you the and symbol, or the ampersand. I can say, give me the address, return the memory address, the address and memory of A. Okay, so this right here now points to A. Okay, so I want to show you something. If we do this, if I print out a PTR, let's see what happens. If I build this and I run it, let's see what happens when I print out a PTR. Okay, you'll see this number here, 0034FD34. It will probably not be the same value on your computer, but this is a memory address. This is a hexadecimal value, and it's a memory address. It's like giving me the address, kind of like the address of an apartment we talked about before. This is the actual address that A lives in. Okay, so I want to show you also, I'm going to clarify a couple things here. I'll say APTR is, all right, and I'm going to say this address of A is, and then I'm just going to directly print out address of A, and we'll see what that prints out. Now, think about what it should print out and see if it makes sense when we print this. Okay. See, they are the exact same, right? 004A F754 and 004A F754. So when the program ran this time, the value A was given this memory address to store the integer inside of it. Okay, so these are the same, right? Because they point to the same thing. Now, if I want to print out the value of A, I can do this. I can say A equals, and I print out A's value. I can also do this. I can indirectly address it by doing this. I can say, I can use what we call the dereferencing operator or the indirection operator. So in this context, I use the asterisk, and I can type A pointer that way. And what that does with the star in front of it is that it says, I don't want just the address like I have up here, that's the variable actually contains that address. I don't want to print out the address. I want to print out what that address points to, what that is at that address. So I'm saying, what does this pointer point to? Okay, and what it's going to give me is what's at that memory location. Not the address itself, but it's going to give me what's at that memory location. So when I say star APTR, it should print out what? Well, what does APTR point to? Well, it points to A. What's at A? 5. So both of these should print out 5, whereas the first two should print out the addresses. Right? And that's exactly what we get. So we see that the first two have the addresses, and then the next two print out the actual value. Okay, so that's your introduction to pointers and indirection. So again, to create a pointer, whether it's to a double, a float, a dog, a cat, or whatever you're pointing to, you use whatever the name of the data type is, and then star. Okay, this is called the pointer. This is called a pointer. To initialize it, you can set it to null PTR, which is a keyword in the C++ 11 standard, or if that does not work, just set it equal to null, NULL, or the value 0. All right. This is the address of, or address operator. Okay, that's the ampersand. In this context, it's called the address operator because it returns the address of its operand. Its operand in this case is A, okay, an integer variable. When I say address of A, it's going to return that memory address that we print out when we have the address of A. Okay, so that's what it returns. Now you'll notice this number keeps changing, right? The number's changing because every time I run the program, it's giving me a new memory address. Okay, I don't decide where this memory address is. The operating system gives me memory to work with from in RAM. Okay, so this is RAM. This is an address in RAM. All right, so that's exactly what we expect. The dereferencing operator, or what we call the process of dereferencing a pointer. This is when you put the star in front of a pointer variable that asks the pointer, what are you pointing at? Not what the address is, but what is at that address. Okay, so I'm not asking it in this case, as opposed to this case, up here where I'm just asking for the address. When I dereference it, I'm asking it, what are you pointing to? So we know that I'm pointing to the address of A. All right. Okay, so that's called indirection. So we've gone over indirection and the address operator. If you want more on indirection, you can look at pages 335 and 336 in the 9th edition of the book. If you're looking for information on the indirection operator, also known as the dereferencing operator, you can look at page 337. We'll go through with a couple other examples. I'm going to look at the example they give in the book on page 339. There are different ways to pass by reference, which we've talked about before. We did pass by value and pass by reference before. So if I want to be able to modify the value when I pass it to a function, I have to put this same symbol here, okay, and that gets a reference to the value, correct? Okay, so what I want to do, though, in this case, is I'm going to show first a pass by value example of getting the cube of a number, and then I'm going to do a pass by reference version using pointers this time. Okay, so I'm going to have int cube by value, and it takes a number. Then I'm going to have void cube by reference, okay, int pointer, let's call it PTR. Oops, I probably should spell things correctly. Okay, so cube by value. This example is going to return n times n times n, because that's what a cube is, correct? So if I have an integer a, and I set it to 5, and remember this name does not have to match this. Okay, neither do these actually. This is just a local variable which will be the parameter when we pass the argument in. This local variable will be used in this way. Okay, so let me just print directly out cube by value. I'm just going to print out the cube by value of a. And let's see if this works. Okay. So when I print it out, it prints out 125, which is what we expect, because this is a pass by value. I take a, which contains the value 5, and then I call cube by value, which uses a local variable n. It just pulls that value in 5, and then it returns 5 times 5, which is 25 times 5, which is 125. So that's exactly what we expect. Now what about cube by value? How do I do this, or cube by reference? Well, in this case, I'm going to take an int pointer called PTR, and this is where things get interesting. I'm going to dereference it because I want to change the value it's pointing to. So whatever I'm passing to it, I want to be able to modify that value. I take that, and then I take the current value that's passed in, multiplied by the dereference of the value, multiplied by the dereference of the value. Now, this really looks complicated. So to clear things up, I could put parentheses around each of these so you can see what's actually going on. Okay, right? So this asterisk in this context is being used to dereference. So I'm saying, for example, when I call it here, if I say cube by reference, and then I pass in the address of a, so I can modify it, then I'm going to print out a itself. We'll see why that's the case in a second. When I pass in that address, I'm saying I want to modify the value at that location, which is a. I'm going to take the value at that location, which is 5 at this point, multiply it by value at the current location, 5, and by the current value at the location, 5 again, and then store it in this location right here. Okay, so in this case, I'm taking the address of a, I'm passing it on to here, cube by reference, and I'm taking the value that is currently at that location, and I'm kind of reusing this variable, and I'm just modifying the value at that location. So let's see what happens when we print out cube by value. Not surprisingly, it prints out 125. Okay, 125. Now, the difference now is that a has actually been modified to be 125. But you notice the difference between this, cube by reference using pointer versus cube by reference using reference, is twofold. I have to dereference the values in here, and I also have to use the address of operator when calling this particular function, right? Okay, so if that doesn't make a ton of sense right now, it's okay. It'll take a while possibly to get used to this kind of stuff. So What I want you to do is look over this code for a couple minutes and then come back, and then we'll talk more. All right? Okay. So we've gone over some of the basics of passing by reference using a pointer, and also what a pointer is. Okay, it's basically a special type of variable which has the memory address of another variable. So there's another big topic within pointers. The topic of pointers called const correctness, or const correctness. This is on page 346, starts on page 346 and goes until about 350. Const correctness is an important thing to keep in mind when you're dealing with pointers, because you may want to restrict certain values and allow for others, or certain behaviors and allow for others. So I also put this in the session notes here. I've got pass by reference. I've got const correctness, and I kind of summarized it here, and this is kind of a nice place to look at. So we use the const keyword in early chapters to inform the compiler that the value of a particular variable should not be modified. So we did explore what a constant is. Okay, so for example, if I have const int a equals 5, or we'll call let's do this. Pi, now let's not do an integer, let's do a double pi equals 3.14159. Okay, that's a constant, because we say it's const. In Java the keyword is final. So I can print it out, right? So I can say what it is if I want to. I can set other values to it. I can print it out. See, it'll print out what value it is. If I want to, I can say if I want, say, the radius of a circle, or I'll say radius is equal to 5, okay, of a circle, and then int area. We don't know what the area is, but we know we'll use r for radius. Let's do this. I can also say area equals, we know that the area of a circle is pi r squared, right? So pi times r, okay, without using the power functions in the math library. I can very easily calculate the area. Okay, so we get that the area is 78. Okay, so it's probably rounded up because I used an integer, but we know it's around 78, so that's good. We can use it. We can use pi as what we call an RHS, or a right-hand value, or RH value. That means we can use it by getting the information out of it, but we cannot modify it. So, for example, if I try to do this, if I say pi equals 5.66, as soon as I try to save that, it automatically gives me an error. It's underlined. So if I try to compile it, it'll tell me what the error is, just louder. It'll say I cannot assign. In the error window, it'll say error pi you cannot assign to a variable that is const. Okay, that seems to have almost a contradictory tone to it, but we call anything that holds memory, or anything that can hold values, a variable. But in this case, we call this a constant, or a const value. And if you hover over it, this may be confusing to you, but it says expression must be a modifiable L value. You might think, what the heck does that mean? Okay, well, what is an L value? I told you that you could use pi as an R value, or an RH value, right-hand value. So that means it can have the value taken from it, meaning you can obtain the value from pi, but you cannot modify it, meaning it cannot be used as an L value, or a value variable that's on the left side of an equation. Okay, so that's why it's flagging this and saying the expression must be a modifiable L value. So if I wanted to set one of the others that isn't a constant, even though that'll truncate the data, I can do that. Okay, all right. So there's just regular old constants. We've dealt with that before. But what about with pointers? Well, constants the const keyword takes on a new meaning when we're dealing with pointers. So there are different levels of access with pointers. In C++, we have several different options for using const with function parameters, okay, with pointers. We should give a function enough access to data, or to the data in its parameters to accomplish its specific task, but no more. This is called the principle of least privilege, which is discussed earlier in the book, I believe. But this is the principle of least privilege, meaning you don't give anything more access to something than it needs to. So for example, with classes, we put the data in the private section of the class, and then we control access to that data. We only allow someone to access data directly, or a function, member function, directly if it absolutely needs to, which is kind of the impetus, or our motivation for using classes. Well, in the same sense, with consts, we have four possibilities with constant data. We have non-constant pointer to non-constant data, non-constant pointer to constant data, constant pointer to non-constant data, and constant pointer to constant data. So it's pretty much every permutation of the pointer and the data being constant or non-constant. Okay, non-constant means it's a regular old variable. Okay, so the highest access level is a non-constant pointer to non-constant data. So this grants the highest access level. Simply declare a pointer without using the const keyword as we've used before. Okay. In this sense, what we're doing is we're giving the function, if we're using a function, we're giving it access. We'll call this, we'll say, my function int pointer p. Okay, and I say void my function int pointer p, and I'll say dereference of p equals 5. That's one thing I can do to it. Just one example of one thing I can do to it. If I wanted to, I could also, I could say, although this is extremely dangerous, I could say int g equals 5, and I could even set that pointer p equal to g. Okay, or actually address of g. All right, so this is one thing I could. These are two different things I could do. It wouldn't really do me one good to do one than do the other, but let's say this, or if I did the first one, if I did dereferenced p and set it to 5, that means that the data that this parameter is pointing to is non-constant, and I'm taking advantage of that fact and I'm changing the value. The other option that I have when I have non-constant pointer and non-constant data is not just changing the data, but changing entirely what it points to. Okay, so I could have a global variable, or I could have another parameter, and I want to point to this right here. And to make it a little more clear, I can even do this outside the context of a function. Let's say I have int g equals 5, and int pointer ptr equals null pointer for right now. And if I say ptr is equal to the address of g, I'm pointing to g first, right? So I can print out the reference of pointer, and it'll print out the contents of g. I can also have int h, and I'll have 10 in there, and let's see what I can do here. I can take the pointer, and now I want to reference h, and then I say dereference pointer again, and what's it pointing to this time? Is it pointing to g, or is it pointing to h? It's pointing to h this time. So I can modify what it points to. Okay, that is because it's a non-constant pointer. Okay, this is the difference between non-constant data and non-constant pointer. So you'll notice that I get two different values here. The first time it prints out the value of g because that's what it's referencing. Then I reset the pointer to point to something else, namely the address of h. And then when I dereference it, it points to the value, or it refers to the value of h. Okay, does that make sense? So I can change the value if I want to. Before I do this, pointing to h, I can change the value of the original G by saying 7, and then I can print out G, and I can even print out the reference of PTR at this point, and I'll get the same value, because they point to the same thing, or they are the same thing. And you notice both of those, originally it says 5, because that's what I printed out before I modified it. I modified the data that this pointer points to because the data itself is not a constant. Okay, I can do that. That's why I can modify the data and make it a 7, okay, which is shown by these two. Then because the pointer is non-constant, I can point to another variable entirely. You can do it with a function or without. Okay, so that's non-constant pointer to non-constant data. That means I can do both. Okay, the second level we can look at is non-constant pointer to constant data. In this scenario, we can't modify the data, but we can modify what it points to. Okay, so for example, let's say I have a function, my function that takes a pointer, but this time it's actually going to take a pointer to constant data. Now, this causes a lot of people problems. Okay, but I'm going to help you try to understand the correct syntax here. You read it from right to left. We could say that P is a pointer to an integer constant. Okay, to an integer constant. So that means that the integer itself is constant, but the pointer is not. Okay, so I'm going to use this. I'm going to say my function const int star P. If I try this, if I try to say dereference of P equals 10, I'm going to get an error. It says the expression must be a modifiable L value, which is exactly what we experienced earlier. That's because the data is constant. However, if I have, say, another constant G, constant int G equals 12, and I want to set P to G, or actually the address of G, then that is acceptable. I can modify what the pointer points to, okay, but I cannot modify the value that it's pointing to. So later on, if I say dereference of P equals 15, that's an error again, because this is a pointer to an integer constant. You cannot change it. You cannot change the value it points to. Okay, you can change what it is pointing to, but you cannot change the value of the variable that it is pointing to. So whatever's at that memory location is constant. Okay, so this, again, this instance is called a non-constant pointer. So meaning you can modify the pointer, what it points to constant data. That means the data at that location cannot be modified. Okay, non-constant pointer to constant data. The next level is constant pointer to non-constant data. In this case, the pointer cannot be modified, but the data it points to can. So in this case, non-constant pointer to constant data, we have, in this case we have constant pointer to non-constant data. In this case, let's say we have this type of scenario. Let's remove the functions just to provide clarity here. Let's say we have an integer pointer constant PTR equals address of x, and we have integer x and integer y up here. Okay, so I'm saying that notice the const is after the pointer symbol here. So what this says is PTR is a constant pointer to an integer. Okay, notice the word constant is not in front of integer. So this means I can modify the integer that it's pointing to, but the pointer itself, I cannot change what it is pointing to. So after I declare this, I can only point to x. Okay, so whatever's at x is the only thing I can point to. So if I say PTR equals 7, is that acceptable or unacceptable? I'm changing the value that the PTR points to. So what I'm saying is I'm setting x's value to whatever this value is here, 7. So let's see if this works. Right? Okay, when I print out x, it did indeed modify that value. However, I will get an error if I try to modify what it is pointing to. So if I say ptr equals address of y, it will underscore it and says expression must be a modifiable L value. That's because the pointer is constant. So constant pointer to an integer. So I can't modify the pointer, but I can modify the data it is pointing to. Okay, so that's the third type, constant pointer to non-constant data. So we've gone over non-constant pointer to non-constant data, which gives the highest access level. Then the two in between, non-constant pointer to constant data, constant pointer to non-constant data. The most restrictive is constant pointer to constant data. This is a scenario in which it's basically what we call strictly read-only. It's minimum access. Okay, so this basically prevents us from doing any kind of modification. So we could go back to our scenario here. We could use it with or without a function. I say const int pointer const. Now what this, again reading from right to left, notice it's a constant pointer to an integer constant. That means the pointer itself cannot be modified and the data it is pointing to cannot be modified. And you'll notice it underlined this because I'm trying to modify the data, and it underlined this because I'm trying to modify the pointer. Okay, so if you want to pass something to a function, then you can use this if you don't want the function to be able to modify it at all, just to be able to use it. Okay, so you can get the value out of it, but you can't actually do any modifications to it. Okay, so that's non-constant, or that's constant pointer to constant data, and then I give you an example of each. So all of these are in the the supplemental materials, the notes that I have posted, and then I also have an additional example down here called selection sort by pass by reference. An array, we have to go over this so you kind of understand what's going on here. An array is a pointer. We haven't really looked at it that way, and it's kind of used in a different way to keep track of multiple items. But really, an array is a memory location. Ultimately, the array, or A, if I were to print out just A, it would point to the first element in the array. Okay? So this is a type of sorting algorithm, which is a very common thing we want to do in computer science, is sorting data. You're taking this jumbled mess of items here, and then you're going through and passing it to selection sort. So what are we saying here? We are saying that we want to have a constant pointer to an integer. Okay, so I don't want to be able to point to a different array inside of here, but I'm going to shift the elements around inside of the array. I'm going to perform a swap. So that's why we're giving it only the amount of access that it absolutely needs. Okay, not just as much as we want. Okay. All right, so that's pretty much it for pointers. Just keep in mind that an array is essentially a pointer. One other thing I want to show you real quick is the size of operator. It's actually kind of useful. The size of operator can determine the size in bytes of a built-in array or any other data type, variable or constant, during program compilation. So, for example, let me do this example here. Let's say integer a to 5. You don't really have to give it a value, but let's say size of cout size of a, and let's see what it prints out. Okay. Notice that it returns 4. Okay, that's because an integer is 4 bytes. All right. What about a double? Let's say double a equals 5.0. We'll say size of a. Print it out. A double is 8 bytes. Okay, and this will actually work with if you create a new class of some sort. It will actually allow you to do that, to take the size. Now, one thing I want you to be thinking ahead about is eventually we're going to be pointing, using pointers to point to objects of classes. Now, you might ask, well, why is that useful? And one of the reasons it's useful is because we're going to be able to reduce the amount of load we're putting on we're putting on a function when we pass an element by reference, as opposed to by value. Let's say I have a dog which has a ton of different integers and strings and all kinds of stuff to describe what the dog is. If I pass it to a function directly, then the runtime environment will have to push all of this data onto the data stack for each element of the dog. It's going to have to put all of that stuff, and it's going to take a lot longer than if I could just pass some little bit of data to the function. So what little bit of data could I pass to it and still have the same effectiveness, still be able to modify or change things or use the object of the class without the overhead of passing the entire object? Well, we just learned about pointers. A pointer in and of itself, even though I told you not to think of them as integers, a pointer is actually an integer, really. So regardless of what it's pointing to, it's an integer because it's a memory location. It's a memory address. So the size of the pointer is 4 bytes. So if we have a dog that's 128 bytes or 256 bytes, would I want to pass the entire dog, the actual object, to the function, or move that around back all over the place, or multiple functions, or would I want to pass a pointer to it? It's much more efficient to pass a pointer to it. So we'll talk about that a little bit later. But that's pretty much all I have for you as far as the pointers are concerned. If you have any questions, which I'm sure you will, this is usually... pointers are probably one of the most complicated subjects for beginners especially, but even seasoned professionals get confused sometimes and forget what they're doing. I didn't cover section 8.8. I would recommend taking a look at it. It's pointer expressions and pointer arithmetic. But don't, and also 8.9 I kind of briefly went over because I'm telling you there's a relationship between pointers and the built-in arrays that we've talked about. I would like you to go over those sections, but we're not going to do anything super intense with that. And they also do a section on pointer-based strings. So this would have been more of an old-school way of making strings. I typically don't personally use what we call character arrays or pointer-based strings very often myself. I don't use them very often. But there's just be aware that it's available, because since we've said that a pointer and array are essentially the same thing, then what is a series of consecutive characters? So if we have an array of characters, what is that? Well, it's a string, right? So I would like you to just look over the chapter and focus on the stuff that we already talked about, and have a great day. We'll talk to you next session.